Hi everyone, I welcome you to the presentation of this video on voltage divider bias configuration under BJTs. So voltage divider bias configuration, the circuit would look something like this. It's going to have a number of resistors. It will have a resistor connected on the base two of them actually, R1 and R2. Then there will be the collector resistor as well as the emitter resistor with excitation, of course, which is VCC going to the ground like that. So when you're given this, how you analyze a voltage divider bias configuration. Of course, before analysis, we have those equations, they still apply. Emitter current is a summation of the base current and collector current. Collector current is basically beta times IB, or in terms of alpha, it's that. VBE is that, VCE is that. These are the same for all the other configurations. So in analyzing, you can split this circuit in such a way that you combine these two resistors so that you just see one resistor. That resistor, you're calling it Thevenin's resistor. And then you get rid of this VCC. Instead, you make the Thevenin's voltage VTH. Your circuit should look something like this now. So this VCC will become ETH, which is the Thevenin's voltage, and then a combination of these two resistors will make this one RTH. That's when you are going to the base like that and then going to the emitter. So make this one, and then that VCC becomes one exciter, which is this one. So you are coming from the excitation voltage, it comes to a combination of those two resistors, then that's when it will go to the ground if you take this route. So from here now we can derive our equations. So you see that from here, what you need to know is what is RTH and what is ETH. So RTH is basically combining these two resistors in parallel. Treat them as if they are in parallel. So when you combine them in parallel, of course, you multiply them and add them. Find the quotient, that will be your RTH. ETH is basically the voltage drop on resistor number 2. So when you find the voltage drop on resistor number 2, basically be resistor number 2 over a summation of the two resistors multiplied by VCC. This will give you ETH. So you're going to have your ETH like that and your RTH like that. Then connect to your transistor. That's when it will go to the ground. So the current which is passing through there, of course, is the base current, and the one passing on the emitter is the emitter current. And then we analyze from here. So from here, if you have to analyze an equation, you will realize that you've got the voltage which is ETH. This one will drop across these parameters. So there will be a voltage drop on RTH, which we are calling IB RTH, which is this one. There will be a voltage drop there, which is VBE. This is the one you're having. And you're going to have the voltage drop on the emitter. The voltage drop on the emitter is that. So you have this. And you can easily do your equations. So this is our analysis, getting this path. And the other path automatically will be this, from supply, passing through the collector, passing through the transistor, through VCE, and then it goes to the ground like that. This is what you are having. So if you use this one is straightforward. You are having VCC dropping there, there, and there. And this is producing that. VCC is equal to the voltage drop on the collector plus VCE plus the voltage drop on the emitter. Then you can easily find whatever they are asking you. So on our next slide, we're going to look at an example. So the question is saying, determine the DC bus voltage VCE as well as current IC for the voltage divider configuration. So when you are given, of course, there will be capacitors, but in DC analysis, DC doesn't see a capacitor. So these will be removed because they will be open circuits. When we begin our analysis, we know that we can take this path where you're combining this, it becomes RTH, and this voltage becomes the ETH. So your path will look like that. So we have a task of finding ETH as well as RTH. So RTH is a combination of the two resistors, this one and this one. When you combine them, they are in kilo ohms. On top, you are going to have kilo ohm squared. Down, you're going to have kilo ohm. Divide kilo ohm squared by kilo ohm to just be kilo ohms. So you may not need to convert. So when you do that, you are going to have that 3.55 kilo ohms. And then you need to find ETH. ETH is the voltage drop across there. So you've got this resistance, which is 3.9 kilo ohms. Down, when you add them, there will be kilo ohms. Of course, when you divide kilo ohms and kilo ohms, they will go. So even here, there will be no need of converting. Just get the figures the way they are. The kilo ohms will cancel. Multiplied by 22, you're going to have 2 volts as your voltage across resistor 2, which is this one. So this is your ETH. So you have ETH, which is 2, you have RTH, which is 3.55 kilo ohms. Then you can find and easily find current IC. So how do you find current IC? we know that ETH is equal to IB RTH plus VBE plus IE RE. From here, we know that IE is basically a summation of two currents, IB and IC. What we are looking for is IB. So you can make IC in terms of IB, for we know that IB is better IB. So now you have all your equation, the whole equation actually is written in terms of IB. From here, you make IB the subject of the formula, you're going to have this. Making IB the subject of the formula, you're going to have ETH minus VBE divided by that. Upon having that, you replace the values. You know our ETH, we know our VBE, and you have those values. When you plug them in there, you're going to have this as the value for the base current. Since we know our base current, it's very easy to find our collector current. Collector current is basically beta times IB. We know our beta is 100, our IB is that. When you multiply them, you're getting that as our solution, which is our current. Okay, so we go to the one where they're asking us to find VCE. For us to calculate VCE, you get that from this one, it's going to produce that equation. VCC is the voltage drop on that, and that. From here, you make VCE the subject. You're going to have this, and then you replace the values there. Upon replacing, where there is IE there, you put a combination of IB and IC. It's going to be that. Multiply that by RE, which is 1.5 kilo ohms. 1.5 kilo ohms is 1,500 ohms. Do your computations there. You're going to produce 12.34 volts as your voltage on VCE. So this marks the end of my presentation on the voltage divider bias configuration. Thanks for watching.